Hello everyone, welcome back to my channel once again. So today we are going to understand acids, bases and salts from class 10th. Okay, and this is a chapter number 2. So before moving forward, let's understand some basic terms. Acids are substances that form hydrogen ions, that is H plus in aqueous form when dissolved in water. For example, hydrochloric acid, that is HCl, gives H plus and Cl minus ions. Okay, and sulfuric acid which gives H2SO4, it has the formula which gives 2H plus and SO4 minus 2 ions. We have one more example here, nitric acid HNO3 which gives H plus and NO3 minus ions. Okay, so now what is the basis? Bases are oxides and hydroxides of metals that react and neutralize acids to form salts and water only, right? So bases which are soluble in water are called alkalis. Not all bases fit into these categories. For example, ammonia. Now alkalis are substances that form hydroxide ions, that is OH minus in aqueous form, that is in water. For example, sodium hydroxide NaOH gives Na plus and OH minus ions. Calcium hydroxide, that is CaOH twice, which gives Ca plus 2 and 2 OH minus ions. So in acid solution, there are more hydrogen ions, that is H plus ions, and than OH minus ions. So that is a acidic solution. And in alkaline solution, there are more OH minus ions than H plus ions. So that acids are dissociated or ionized to large extent are strong electrolytes and called to be strong acids. When acids that dissociate only to a small extent are called weak acids and weak electrolytes. Okay, so bases can be strong or weak, same as strong acid and strong base. Strong acid and strong base, and strong base and weak base, right? So bases can be strong or weak depending upon what? On the extent to which they dissociate and produce OH minus ions in solution. Means they are breaking and making the OH minus ions. If OH minus ions having the more quantity, that means it shows the strong base. Most metal hydroxides are strong electrolytes and strong bases. Ammonia, that is NH3, is a weak electrolyte and weak base. Now, it is a number of ionizable H plus ions present in an acid. For example, HCl is monobasic. It ionizes to produce one H plus ion. Okay, HCl which gives H plus plus Cl minus. Now, H2SO4 is a dibasic. Means, first of all, understand why it is said to be monobasic. Means we need one more OH minus ion, only one, because we have one H plus. So for that ionizing, we need only one OH minus ion. That's why it's said to be monobasic. Now, why it is said to be for H2SO4, that is a dibasic, because here we are getting two H plus ions. So for that we need two OH minus ions. So H2SO4 which gives rise to two H plus plus SO4 SO4 minus 2 ions. Okay. Now the third point is H3PO4 is tribasic. Here you can see three hydrogen ions. So it ionizes to produce three hydrogen ions. Now the one more example is H3PO4. Same here, again we are getting 3H plus plus PO4 minus 3. So again it is tribasic. And this is called to be basicity. Now acidity of a base. Acidity of a base, we just saw about the basicity of a acid. Okay, so here it is ionizable OH minus present in an alkali. Means how many OH minus are present in a base, which define as acidity of a base. Now NaOH is monoacidic. Why it is only it's said to be monoacidic? Because we can see OH minus, that is a 1 in quantity. Okay, we have only one OH minus ion. That's why it's said to be monoacidic. Now CaOH twice is diacidic because we have two OH minus here. Let's see some common strong acids and their anions. Okay, common strong acids and anions of these strong acids. Now HCl formula it is given and the name is also given. Okay, and the ion is also given. From HCl we are getting Cl minus, that is chloride ion. Then HBr Br minus, that is bromide ion, Hi, that is I minus iodide ion, HNO3, NO3 minus nitrate ion, then HClO4 perchloric acid. So here ClO4 is a perchlorate ion we will get. Now HClO3, that is chloric acid. So we are getting ClO3 minus chlorate ion. And H2SO4 we are getting sometimes HSO4 minus, that is hydrogen sulfate ion, and sometimes we are getting only sulfate ion, that is SO4 minus 2. Now common weak acids and their anions. Okay, again HF, that is weak acid, whereas HCl, HBr and HI are strong acids. Okay, just a minute. So we are getting from HF, that is hydrofluoric acid, we are getting F minus, that is fluoride ion, then acetic acid, CH3COO minus, that is acetate ion we are getting from HCN, we are getting cyanide ion, Cn minus, HNO2, where we are getting NO2 minus, nitrite ion, then H2CO3 carbonic acid, we are getting sometimes H3, it depends on the solvent, H3O minus hydrogen carbonate ion, and CO3 minus 2 carbonate ion. Okay, and a sulfurous acid, that is H2SO3, sorry, H2SO3, that is sulfurous acid, and H2SO4, that is sulfuric acid. Okay, this is a different. So you can pause it and read it. Now, how we are giving the name to the acids? Okay, so there are binary acid, ternary acids, right? So binary acids which has H plus and a non-metal. Okay, which has H plus and non-metal. So hydro, that is non-metal, hydroid plus ic acid. So here HCl, that is hydrochloric acid. That's why hydrochloric acid, non-metal, chlorine is a non-metal, right? Now ternary acid, H plus and polyatomic ion. Okay, H plus and polyatomic ion. So here we are having polyatomic ion 8 plus ec acid, that is HNO3 aqueous, that is nitric acid. Now polyatomic ion, one more type of is here, ide plus ec acid, that is HCN, that is cyanic acid. Okay, cyanic acid, and one more is here, polyatomic ion EAT plus us acid. So the example is nitrous acid. Now, how we are writing the formula of acids? So, acids formulas get written like any other. Write the H plus 1 first. You have to write out that H plus 1. Then figure out what the negative ion is based on the name. Right? Cancel out the charges to write the formula. Don't forget the aqueous after it. You have to put that. It's only an acid if it is in the water. That's why we have to show it is in the water by writing aqueous in bracket. Now carbonic acid, which has H plus 1 and CO3 minus 2. So that time you will write H2CO3. That minus 2 is showing, is representing the how many H plus ions are present in the acid. Now, chlorous acid, H plus 1 and ClO2 minus 1 means only one H. So that's why we are writing HClO2 aqueous. Then hydrobromic acid, H plus 1 plus Br minus 1. So same, only one H is there, that is HBr, which is in aqueous form. So what will be the for this hydronitric acid? How many H plus and how many nitric this one ions? So coming down. Next, properties of bases. Bases react with fats that to form soap and glycerol. Okay, bases react with fats to form soap and glycerol. This process is called saponification. Bases have a pH of more than 7. Dilute solutions of bases taste bitter. Bases turn phenolphthalein pink, litmus blue, and bromothiamyl blue into blue. Okay, now bases neutralizes acids. Bases are formed when alkali metals or alkaline earth metals react with water. The words alkali and alkaline mean basic as opposed to acidic. Now, how we are naming the bases? Bases are named like any ionic compound, the name of the metal ion first with a Roman numeral if necessary, followed by hydroid. Now, FeOH twice, which is in aqueous form. So we have to write the first the metallic name, that is here iron. Okay, and we are showing the Roman numbers. Okay, how many hydroxides are present in a Roman number. So iron 2 hydroxide. Now here then FeO3 aqueous, you will write iron in bracket 3 hydroxide. Same way you will follow this. Now AlOH twice, aluminum hydroxide. Okay, this is also uh, number 3 is missing, right? So you will write the same thing as NH4OH also. Next, how we are writing the formula for bases. Formula writing of bases is the same as for any ionic formula writing. The charges of the ions have to cancel out, right? Now, calcium hydroxide, we are having here Ca plus 2 and OH minus. So again, it is showing the how many OH minus are present. Now, CaOH twice, Ca plus 2 means there are two ions of OH minus are present. Now potassium hydroxide K plus 1 and OH minus, that is KOH. Charges are cancelling here. Then lead 2 hydroxide means Pb plus 2 and OH minus. So you will write PbOH twice. Okay. So I have given some homework also. You will write that in comment. Now, what are the physical properties of acids and bases? First of all, acids. Acid tests are, that is, for example, vinegar, lemon juice. Acids are harmful to living cells. Aqueous solutions of all acids contain hydrogen ions. Acid turns blue litmus red. B2 red, you will remember like that. B2R. Now, strong acids are corrosive, which damage to the objects. Now, bases. Alkalis are taste bitter. Strong alkalis are corrosive. Aqueous solutions of all alkalis contain hydroxide ion, that is OH minus. Don't be get confused in hydrogen ion and hydroxide ion. Okay, they are different, like their names are also different. Alkalis turn red litmus to blue. Okay, in acids, litmus turn blue to red, but in alkalis, that is in bases, red to blue. It is reverse. Soapy touch. Let's see chemical properties of acids with metals. First one, metals above copper in the reactivity series will react with acids, giving off hydrogen gas, forming a salt. So let's see the reaction. Mg, which is solid in state, plus H2SO4, that is in aqueous form, which gives rise to MgSO4, that is in aqueous form, plus H2 gas. With bases, metal oxides and hydroxides, the base dissolves in the acid and neutralizes it, a salt is formed. So in first reaction, what is the salt? Comment down. H2SO4 aqueous plus CuO in solid form, which gives rise to CuSO4, which is aqueous form, plus water. With metal carbonates, effervescence occurs. Salt, water, and carbon dioxide gas is produced. Effervescence means bubbles occurs. The reaction is 2HCl plus CaCO3 gives rise to CaCl2 plus H2O liquid, that is water, plus CO2 gas. Okay, so this is about neutralization. H plus 1 plus OH minus 1 gives rise to water only, right? Here we are having H plus ion plus OH minus 1, which gives rise to water only. But what is the neutralization process? When acid plus base, which gives water and salt. So that is a neutralization process. So we have here examples: HCl, that is acid, and NOH, that is base, which gives rise to water, plus NaCl, that is a salt. Now one more example is here. H2SO4 is acid plus KOH, which is base, which gives rise to two molecules of water, plus K2SO4. So I have given you some examples to solve. You can comment that. Formation of hydronium ion, that is H3O plus. The hydrogen ion H plus does not exist as such in aqueous solutions. So hydrogen ions combine with water molecules to give a more stable species, that is hydronium ion H3O plus. So for example here HCl plus H2O, which gives rise to H3O plus, that is a hydronium ion plus Cl minus ion. Now acids can contain different number of acidic hydrogens, right? And can yield different numbers of H3O plus ions in solution. So here we have sulfuric acid, H2SO4 aqueous plus H2O, that is water, gives rise to HSO4 minus aqueous plus hydronium ion. We have one more example here, means this reaction is again continuous. Okay, the first one. Now, whatever we are getting the HSO4, that is sulfurous ion, okay, HSO4 minus aqueous, again it reacts with the water and it gives rise to SO4 minus 2 aqueous ions plus H3O plus aqueous ion, that is hydronium ion, and this reaction is reversible. Now, all these reactions are reversible. They are giving the stable hydronium ion. Okay, now phosphoric acid, that is H3PO4 plus H2O, which gives rise to H2PO4 plus minus plus H3O plus. Okay, again the same reaction is happening with the water molecule. So here we are taking three molecules of water and we are getting H3O plus stable ion. So what are the uses of acids? So first of all, HCl in stomach. Okay, then the second one, H2SO4 in car batteries as drying agent, then HNO3 in manufacturing of fertilizers, then ethanic acid in food industry, we are using this one, then next fatty acids in soap making, and ascorbic acid in medicines. Now let's see chemical properties of bases. First one is a neutralization. Second, ammonium salts are decomposed when mixed with a base. Decompose means we are just destroying it, right? So a base, for example, sodium hydroxide NaOH, okay, and the ammonia is readily detected by its pungent odor. Pungent means spicy odor, that is strong smell, and by turning damp litmus blue. Okay, so NOH, that is sodium hydroxide plus NH4Cl, ammonium chloride, which gives rise to NaCl, that is a salt, table salt, plus H2O plus ammonia gas. So ionically NH4 plus OH minus, which gives rise to H2O plus NH3. Right? This is a formation of ions from NH4OH. Next, this reaction can be used to prepare ammonia gas and as a taste for an ammonium salt. Now, alkalis are used to produce the insoluble hydroxide precipitates of many metal ions from their soluble salt solutions. So here we have example of 2NaOH plus CuSO4, which gives rise to Na2SO4 plus CuOH minus OH twice. So ionically, how we are getting CuOH twice? So first of all, we have to take Cu plus 2 ions plus 2OH minus ions, and we are getting CuOH twice. So this reaction can be used as a simple test to help identify certain metal ions. Now, types of oxides. Basic oxides on the left and the middle of the periodic table are the basic metal oxides. Where are they situated? On the left and the middle of the periodic table. Now, for example, Na2O, MgO, CuO, etc. So they react with acid to form salts. First one is HCl plus MgO, which gives rise to MgCl2 plus H2. MgCl2 plus H2. Then second one, CuO plus H2SO4, which gives rise to CuSO4 plus H2. These metal oxides tend to be ionic in bonding character with high melting points. As you move left to the right of the periodic table, you will see oxides become less basic and more acidic. Types of oxides. Here basic acidic oxides on the right of the periodic table. Okay, we have basic oxides left of the periodic table and acidic oxide right of the periodic table. The acidic oxides of the non-metals are present, for example CO2, P2O5, SO2, SO3, etc. So these tend to be covalent in bonding character with low melting and boiling points. Those of sulfur and phosphorus are very soluble in water to give acidic solutions, which can be neutralized by alkalis to form salts. So we have SO2 plus H2, which we will get H2SO3. Then SO3 plus H2O, we will get H2SO4. Types of oxides. First of all, amphoteric oxide. They are metallic oxide. They react with both acids and alkali. That's why it's said to be amphoteric oxides. They are usually relatively insoluble and have little effect on indicators. For example, aluminum oxide dissolves in acids to form normal aluminum salt like the chloride, sulfate, and nitrate. However, it also dissolves in strong alkalis like sodium hydroxide solution to form aluminate salts. Neutral oxides, they are non-metallic oxide. They tend to be of low solubility in water and have no effect on litmus. That's why they said to be neutral. We know that. We do not react with acids or alkalis. For example, CO, carbon monoxide, and NO, that is nitrogen monoxide, and H2O, that is water. Water is also a neutral in nature. There is no way of simply predicting this kind of behavior from periodic table patterns. We have to test them. Periodic trends in oxides, increasing acidic order, okay, from left to right and from top to bottom, increasing base character. Next, salts. When H plus ion of an acid is replaced by a metal ion, a salt is produced. H2SO4 plus 2 NaOH gives rise to Na2SO4 plus H2O. Here, sodium sulfate, that is Na2SO4, is the salt formed, and salts are ionic compounds. Okay, so ammonia, that is NH3, is an unusual base. It does not contain a metal. It forms aluminium salts containing the aluminum ion, that is NH4 plus, right? So NH3 plus HNO3, that is ammonium nitrate. Sorry, NH4NO3, that is ammonium nitrate. We are getting the salt. Now, methods of making soluble salts. So there are, first one, acid plus metal, which gives salt plus hydrogen. Then acid plus base, which gives salt plus water. Then acid plus carbonate gives rise to salt plus water plus carbon dioxide. Then acid plus alkali, which gives same, salt plus water. Right. Then direct combination. So the first method, acid plus metal. So not suitable for making salts of metal above magnesium or below iron or tin in reactivity. So for example, zinc plus 2 HCl, which gives rise to ZnCl2 plus H2, right? Then second one, Fe, that Fe plus H2SO4, which gives rise to FeSO4 plus H2. Method 2, that is acid plus base, useful for making salts of less reactive metals, for example lead and copper. So we will think and which method we are using according to the reactivity. So first one is CuO plus H2SO4, which gives rise to CuSO4 plus H2O, MgO plus 2HCl, which gives rise to MgCl2 plus H2O. So add excess base to acid here. Now, method 3, that is acid plus carbonate, useful particularly for making salts of more reactive metals, for example, calcium and sodium. So, we have example CaCO3 plus 2HCl, which gives rise to Cl2 plus H2O plus CO2, that is carbon dioxide as gas. Then Na2CO3 plus H2SO4, which gives rise to Na2SO4 plus H2O plus CO2. Method 4 is there, alkali plus acid plus alkali. So this is useful for making salts of reactive metals and ammonium salts. So it is different from method 1 and 3. As both reactants are in solution, this means neutralization must be achieved by adding exactly the right amount of acid here to neutralize the alkali. This can be worked out by titration only. So NaOH plus HCl, which gives rise to NaCl plus H2O, then 2NH4OH plus H2SO4, which gives rise to NH4 twice SO4 plus H2O. This is a titration diagram. Now, making insoluble salts. This involves mixing solution of two soluble salts that between them contain the ions that make up the insoluble salt. It is made by two methods. First one is precipitation, then second one is the direct combination. So for precipitation, we have example BaCl2 plus MgSO4, which gives rise to BaSO4 plus MgCl2. Now the second method is direct combination. We have to do direct combination of Fe plus S, which in the heat, and we are getting FeS. Okay, so precipitation reaction. So there are some types of salts. Normal salt, how we are getting. Normal salts are formed when all the replaceable hydrogen ions in the acid have been completely replaced by metallic ions. Okay, so this is type of a one replacement reaction only. So HCl plus NaOH, only we are changing the, means replacing hydrogen ions with the metal, right? So NaOH, just we are just changing OH and we are just putting Cl there only, that's it. So NaCl plus H2O. The in H2SO4 Zn, H2SO4 plus ZNO, what we are doing, just changing the place of the ZnSO4 and we are getting ZnSO4 plus H2O. The normal salts are neutral to litmus paper. So acid salts. Acid salts are formed when replaceable hydrogen ions in acids are only partially replaced by metal, not totally. Acid salts are produced only by acids containing more than one replaceable hydrogen ion. So, therefore, an acid with two replaceable ions, for example H2SO4, will form only one acid salt, while acid with three replaceable hydrogen forms two different acid salts, that is H3PO4. So, for this purpose, for getting acid salts, we need more than two hydrogens in the acids. So, H2SO4 plus KOH gives rise to KHSO4 plus H2O. Then H3PO4, which gives plus NaOH, gives rise to NaH2PO4 plus H2O. Then H3PO4 plus 2 NaOH gives rise to Na2HPO4, like that. So an acid salt will turn blue litmus to red in the presence of excess metallic ions. An acid salt will be converted into a normal salt as its replaceable hydrogen ions become replaced. Now, basic salts. Basic salt contain the hydrogen ion, that is OH minus. They are formed when there is insufficient supply of acid for the complete neutralization of the base. A basic salt with which will turn red litmus to blue and will react with excess acid to form a normal salt. So ZnOH twice plus HCl, which gives rise to ZnOHCl plus H2O, and remaining examples are there. Just a minute. Now, hydrated and unhydrated salts are there. Yes, we are correct. Hydrated salt mean which having the water in it, right? So you can see the example. CuSO4 5H2O, which contains 5 molecule of water. So that is hydrated salt. Okay, there is a presence of water in the salt. So salt that contains water of crystallization is called hydrated salt. For example, CuSO4 5H2O, Na2CO3 10H2O. Okay. Now second one, unhydrated salt, right? So opposite to hydrated salt means absence of water. Salt with an out of water crystallization, water of crystallization is called unhydrated salt. So examples are CuSO4, Na2CO3. So you will have the some crystal hydrates only. Salt hydrate means water containing, okay, which is, you can read this. So we have here hydrate crystals, carbon cobalt nitrate, calcium nitrate and nickel sulfate. From the top you can see, from you have to go left to right, right? Then the manganese sulfate, copper sulfate, that is blue in color, anyone can identify, and chromium potassium sulfate, that is last one, which is dark brown in color. So uses of what where we are using the salts, right? So ammonium chloride we are using in torch batteries, ammonium nitrate we are using in fertilizers, calcium chloride we are using as a drying agent, then iron sulfate we are using iron tablets, that is in medicine, magnesium sulfate again in medicine, potassium nitrate in we are using it is in a gunpowder, then silver bromide you may have know about this, we are using in photography, then sodium chloride, that is a making NaOH, even sodium chloride, that is NaCl, that is a table salt. Sodium stearate in making soaps. So self ionization of water means how water is making, means how water is making ions itself. So we need for this a pure water is often used as example for non-conducting liquid, right? So in fact, water will conduct electricity if there is sufficient electrical energy present. The fact that pure water conduct electricity suggests that it contains ions, right? So the ions present are due to water undergoing self ionization. How? So now for this we need two molecule of water, and we are getting H3O plus, that is hydronium ion plus OH minus ion. The concentration of H3O plus ions in pure water at 25 degrees Celsius is how much? Is 10 raised to minus 7 moles per dm cube. The concentration of OH minus ion should also be 10 raised to minus 7 moles per dm cube. So the pH scale for acids and alkalis, you can see where it is weak and where it is strong. So when once you are moving towards from 7, 7 is a neutral, okay, this it starts the from 7 only. When you go towards 1, that will be strong acids from the 7, and when you go after the 7, okay, towards 14, that will be strong base. On pH scale, we will see the numbers only 1 to 14, that is you have to remember. Now, the pH scale is a measure of relative acidity or alkalinity of a solution, and it is defined as negative log of H plus ion concentration, and we have the formula pH is equal to minus log H plus ion. So water is the neutral liquid with a pH having the 7, that is green in color, which shows when a substance dissolves in water, it forms aqueous solution that may be acidic, may be neutral, or may be alkaline. So acidic solutions have pH of less than 7, and which are having lower the number, the stronger the acid. Then neutral solutions have, means when your pH is 1, that means it is strong acid. Now neutral solutions have pH of 7. So these are quite often solutions that is of salt only, which are themselves formed from neutralizing acid and base. Then alkaline solution, that is basic, which have pH of over 7, that is higher than pH. So, okay, so it will be if pH is more, so that alkali or base will be strong base. Weak alkalis like ammonia, which having the pH 10 to 11, but strong alkalis like sodium hydroxide, which gives pH 13 to 14. This is a again pH scale. A change of 1 in pH is tenfold increase in acid or base strength. Okay, a pH of 4 is 10 times more acidic than pH of 5, and a pH of 12 is 100 times more basic than pH of 10. pH range for a few common substances what we are using in our day-to-day life. Now gastric contents, which is present in our stomach, which has the pH range 1.6 to 3, that is more acidic. See, look at the arrow also. Then soft drinks, which are again 2 to 4, lemons 2.2 to 2.4, then vinegar 2.4 to 3.4, tomatoes 4, yes, tomatoes which shows the acidity, that is 4 to 4.4, beer which shows the 4.4 to 5, then urine, then 4 to 4.8 to 8.4, milk, that is cow's milk 6.3 to 6.6, again saliva 6.5 to 7.5, blood plasma which shows 7.3 to 7. Mean it is showing the little basic, that is neutral actually. After the neutral, it is showing not exactly 7. Egg white, it is showing 7.6 to 8. Milk of magnesia 10.5. That's why we are using the antacids which is present. Means in antacids, milk of magnesia present. We are using when we are feeling the acidity, right? To neutralize it. Then household ammonia, we are which shows 11 to 12. Means little bit more basic. So indicators we have, so there are some common indicators we use: methyl orange, bromothymol blue, phenolphthalein, and screened methyl orange. So in color in strong acid which shows methyl orange shows red and pH shows 4, and color in alkaline solution, that is strong base, which shows yellow. Then next one, the it shows yellow and pH is 7. Yes, shows still it is showing the colors and blue. Then phenolphthalein, it shows in strong acid colorless with pH 9, and in base it shows the red. Okay, now screened methyl orange, it shows red in acidic acid and not acidic acid, acidic solution, and pH shows 4, and in base it shows green. You can see the examples here with the pH scale. Now, this is also about pH graph. Now, ionic equations. In many reactions, only certain ions change their chemical state, but other ions remain in exactly the same original physical and chemical state. So, such type of ion, where they do not change, are called spectator ions. The ionic equation represents the actual chemical change and omits the spectator ions. To write a net ionic equation, we need a balanced molecular equation. Then rewrite equation showing the ions that form in solution when each soluble electrolyte dissociates into its component ions. Only dissolved strong electrolytes are written in ionic form. Identify and cancel the spectator ions that occur unchanged on both side of the equations. Then you can write the correct symbol also. Now, scheme for ionic equation. So how we will think about it. So first of all, is it soluble in water? If it is yes, it is mostly either ionized or dissociated in water. If it is S, then write equation in the ionic form H plus Cl minus, for example, because HCl is completely ionized. Or another example, that is Na2SO4. If it is not soluble in water, you have to write the full formula, that is PbSO4. We are taking the example. Okay, and again, if it is not either ionized, we will think about the next example, that is CH3COH, that is acetic acid. In this way, we have finished this lesson. I hope you understood about this lesson about the acid, base, and salts in detail. Okay, if you like this video, subscribe my channel. Thanks for watching.